So a week from today, and from circular motion to rotational motion. So in circular motion, a point object is going around in a circle, but in rotational motion, the whole object could be spinning, rolling, and so on. So that's the difference there. Although some of the characteristics are shared in that case. Okay. So in our note, you can see that here, dynamics in vertical circle, and this is an example problem where this roller coaster is going in this vertical circle like that, okay? So the speed could be different at different point. In practical application, that's what happens. But sometimes you may be also asked, the speed is same all over. So for that, you have to have some sort of forced rotation. But no matter how the speed is same or different, we can use the same idea that if we know speed at any point, we can write the equation for radial acceleration. So that means if it is here, there always going to be a component of acceleration or acceleration pointing towards the center, right? And those accelerations are called radial acceleration, and their value is given by v square over r. So that is speed at the point. Okay, so if speed is changing, you need to keep track of what the speed is at those particular points. If they are not changing, and then that's great. It is same everywhere. If you know in one place, you know everywhere. Okay, so this is radial acceleration. So even if it's not pointing towards the center, sometimes the acceleration may be pointing slightly off from the center. Then you can always find the component towards the center. Maybe it's easier if I show it here. So let's say rather than pointing like that, it is pointing slightly off. So in that case, you can find the radial acceleration component of that in that direction. Okay. And they're going to be tangential acceleration. So for this, we are talking about just the radial acceleration, and that radial acceleration is always equal to speed at that point squared over r. So that you want to keep in mind. Okay. So now how do we solve problem when something is moving in vertical circle where speed may be changing? Okay. So just like solving any dynamics problem, you need to draw free body diagram, and that's what I'm doing here. So here the roller coaster is in the inner part of this track, so that's why the normal force is down, and of course mg is always vertically down, but in this case normal force is also down. So that is the free body diagram. And we are planning to use Newton's second law in radial reaction. So that means we need to define what is radial reaction. And that is towards the center of the circle. So in this case, see, center is pointing right in that direction. So that means we can say, okay, that is the r axis. And let's say down as a positive. So why here we are choosing down as a positive? We don't have to, but I'm choosing down as a positive because I want to choose positive in the direction of acceleration. Since the acceleration value is this, its direction is always towards the center of the circle. So at this point, center is in that direction, so this acceleration is also pointing down. So acceleration is pointing that way means I'm choosing positive that way. So when I write that equation for the acceleration always going to be positive in the equation that way. So even if we forget to write correct sign, maybe our equation is still going to be correct equation, right? And so that's why I am, choosing that. But of course, you can choose up as a positive. But of course, direction of acceleration is down. So in that case, your equation, intermediate equation, gonna be different, but the final result gonna be same because choice of coordinate does not change the physics. We need to keep that in mind. So once we have that, what do? We now need to write sum of the forces in radial direction. And there are two forces pointing in radial direction. And since we chose down as a positive and both of these forces are pointing down, we have both of these positive here. So this is the left-hand side of this equation. And right-hand side is this mass times acceleration. And that's what I'm writing. Mass and acceleration is v squared over r. So that's what you see. And since the acceleration is also in positive direction by construction, this is also positive. Although I did not write that positive explicitly, these are all positive based on our choice of axis. Okay. If you have if you had chosen up as a positive, then all these being down, all these would be negative. And you can say, okay, all these negative cancels, giving you positive. So result would still be same. Okay. So that's how we write the equation. And depending on what we want to solve for, we can solve that. So in this case, it says find the apparent weight. So whenever you are asked to find apparent weight, you finding for normal force. Okay. So that we learn in the class in the circular motion. So this being review, I'm just reviewing in little detail here. And now here is a question for you. Okay. So in this case, what is, let's say just the apparent weight of mass. Probably I don't even need to write equation in the question. So I'm opening the poll. Go ahead, draw a free body diagram, write down the equation, and choose the answer, okay? So you have 2.5 minutes to answer this question. Are you drawing free body diagram? And are you writing this equation first? And then expanding it, just like we did in that last slide. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do here. So mostly C, but there are B and D as well. Nobody chose A, that is good, because A is not correct answer here. So let's draw a free body diagram here. Oh, looks like I need a bit more room here. So weight is always vertically down, but this time normal force is up because it is being supported by this side here. So the normal force is there, okay? And it does not talk about friction force or anything like that. So there are only two forces acting there. Now center of the circle is over here. So that means acceleration is pointing in that direction. Which acceleration? Radial acceleration that we are interested in. So radial acceleration is pointing up. So because of that, let's choose up as a positive. Okay, in this case. So when this was down, we chose down as a positive because the acceleration points towards the center, remember, always. So we chose down as a positive, same as the direction of acceleration. If object is here, then the acceleration gonna point it this way, so you wanna choose this way as a positive, and so on. So that's how it works. Okay, so with that, now let's expand this. Oh, this is axis, our radial axis, right? So rather than writing, we were writing something like this, or y for the translational motion. For circular motion, what do? We replace x by r because we want one axis always in the direction of radius of the circular path. And why is that? Because when something is moving in circle or part of circle, it always gonna have a component of acceleration pointing in that direction. And that's what we want to make use of by writing this equation. So that's what we are doing, okay? So with that, so sum of forces in radial direction. So there are two forces. Normal force is pointing up, and since we chose up as a positive, so normal force is going to be positive. And then mg is pointing down, so it's going to be negative now. So since there are two forces, sum of all forces in radial direction means just sum of these two forces. And that's what we did. So that means left-hand side of this equation is done. Now we're going to move to the right-hand side of the equation, which is mass. So we just copy mass, and radial acceleration is speed at that point divided by speed square divided by r. And in this case, by construction, we are choosing positive in the direction of acceleration, means this always going to be positive if you are choosing the axis wisely, okay? Or this way. I wouldn't say, if you choose axis down is not wise, as long as, you can tell what's going on. So now the apparent weight is asking. So that means we are solving for n. So that means we need to move this mg to this side. When we do that, both of these are going to be positive, means it's going to be C. Okay. So that's why C is correct answer. Okay. So basically, there is just the difference in positive versus negative while using equation. Only that's the difference. Okay. Now, here is another question related to this. So a very similar problem I have done in the note as well. So this bicycle, they are turning. So that means they are moving in part of circle, just like I'm showing it here. And the normal force is now acting something like that, okay? So that's why that is that. So it makes an angle with the particle. So I'm showing that angle something like this, okay? So now the question is, which equation represents the application of second law of motion of a cyclist in a circular path? So whenever we are looking at equation in circular path, we are looking at in radial direction. So basically here I already gave you positive axis. So use that to write this equation. So we need sum of forces in that direction. So it looks like there is no forces in that direction. But this force over here, on the other hand, let's say if we choose this one, this as one axis, then another axis has to be this, because two axes we want perpendicular. So the n is neither along the radial direction or vertical direction. So you need to find component of that and use that to apply the equation, same equation. Okay. So now with that said, I'll let you work on this and pull on this. So you have, again, 2.5 minutes to complete this. Meantime, I'm gonna go grab water for me. It looks like I did not bring water. Oh, it's here. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got here. So we have varieties, but mostly C. I don't know the answer, so let's do it. So just like I said before, we need to write the component of N. So the angle being over here, this is going to be cosine component of that normal force. And this, so rather than drawing over there, another component, we want to draw it here because we want to draw everything starting from this dot in a free body diagram. So this is N sine theta. Maybe if I write over here, it's easy to see it, right? So now when we use this equation, we are just looking at this reduction. So there is only one force. And remember, the acceleration is also pointing in this towards the center of the circle. So that means it's going to be positive n sine theta. So only one force in that direction. Okay, so the mg is perpendicular, which is in that direction. So we don't include that there. So that is equal to positive mb square over r, because ar by construction is also positive. Okay. Now, if you are thinking, okay, what if I used this and try to find the equation, write the equation, it just says the equation, write an equation. Okay, let's do that one too. So along the vertical direction, we can do sum of forces along the y direction. And since it is not accelerating in vertical direction, it has to be zero. It is in equilibrium along the vertical direction. So that means it's going to be positive n cosine theta, assuming up as a positive here, okay? And then mg is negative, and right-hand side is 0. So that means it's going to be n cosine theta is equal to mg. And now we can combine these two equations to solve things we are looking for. So we have two equations, but in this case, you see, we don't have any of choices that looks like this, okay? So definitely it was used in that direction. Okay, with that said, looks like it's time to take break. So let's take break and I'll see you in 5 minutes. Okay, so after the dynamics, we started talking about work done, because work done is the process of transferring energy, and conservation of energy involves the energy. So that's the direction we are moving towards, right? So finding work done is important, and this is vocabulary, right? So vocabulary that comes with an equation and some baggage. Means there is this angle here in the definition, which is the angle between force and displacement. So that's why you need to draw force and displacement, and only that the one angle you want to use in this equation. If you use, for example, let's say if this angle is given, and if you use this angle in that formula, then that's going to be wrong. Okay, so that's why we said, okay, let's draw FD diagram. And how do we read this equation? Work done by a force is equal to the product of the force, displacement caused by the force, and the angle between the force and the displacement. Okay. So those things very important. Keep that in mind so that you can correctly find the work done. Okay. So you have to first identify, okay, I'm finding work done. Work done by which force? What force? Right? So you need to ask that question. So once you know what force you are talking about, you need to figure out what direction that force is acting and draw the force. And then finding direction of displacement, not going to be that bad. So for example, if displacement is going something like that, then the angle going to be this angle, and we know this angle is 90 degree. So that's the angle that goes in the cosine theta, because the cosine of angle between force and displacement. So when that happens, cosine 90 is 0. And just for your convenience, I have written them here. So I'll be asking some question. Maybe you want to copy this if you don't remember, so that you can use it without having to use calculator. So always a force does the work, and work done by that force is product of the force times displacement caused by that force times cosine of angle between them. Them here means the force that's doing work and the displacement. Okay. Okay, with that said, now it's your turn. So you lower a book of mass m downward, and distance is given, and speed is constant, it says. And now work done by the force of gravity, they are asking. So draw F and D and figure out angle and use that formula. Remember, work done formula is FD cosine theta. That's the general formula. So you need to identify what force, what's the direction of displacement. And then if you draw them, that's going to give you angle. And that way you can use that. Remember, in this formula, we don't use sign of the force and displacement. We just use value. Sign is taken care while drawing them, and the angle gives that angle takes care of the direction. So that's why we have to be very careful about what angle we are using. Okay? So with that said, I'm opening the pool, and you have 1 minute and 30 seconds. So go ahead, draw F and D for this particular case. Figure out angle and use the formula. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So mostly B. but there are some A and C as well. So work done by gravity. Gravity always does negative work. Is that correct? I don't know what you are thinking, but I don't want to remember like that. I want to remember this technique and use it. So in this case, force of gravity means it's always acting vertically down. And the displacement, since you are moving this downward, displacement is also down. So the angle between them is 0 degree because both of them are pointing down, means when two lines pointing to things pointing same direction, the angle between them is 0 no matter what direction they are pointing, as long as they are pointing in same direction, right? So in this case, so downward, so D is H. Okay, so in this equation, there is no speed, so speed does not matter. So that gives me this formula, work done as mg times h times cosine of angle between them. Cosine 0 degree is positive 1, means the work done is positive mgh. So looks like A is correct answer in this case. See, a lot of you made mistake. What happened? Anything you like to add or ask on this one? Well, then let's move on. I have another question for you now. I'm pulling for this. And again, you have a minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see how did we do. So there are many B's this time. Again, I don't know the answer. That what I'm gonna do is I'm gonna draw like this. This time we are lowering something, means we are applying force upward. So the applied force is gonna be upward. And displacement is downward. So that means angle between them is 180 degree. So work done is FA times displacement, which is H, and cosine 180 degree, and that gives us -1. So that means it's going to be negative applied force. So if you are lowering with constant velocity, the force, both of these forces are balanced. mg is down, F applied. Okay, so they are equal. So if you like, you can replace this by mg, and h is there. So this is negative work done, and that means, oh, that is B. So this one, most of you got it right. Great. So now let's look at one more question. So now we are pulling on this one here. The net force on the book, work done by net force. Again, you have 1 minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see. So mostly C in this case. I suppose that is correct answer. So in this case, two forces are balancing. How do we know? Because moving with constant speed. So F net is 0. So how do I draw a free body diagram of net force? 0. I just put dot, and this is displacement. So since the force itself is 0, when we plug in that force in this equation, we get 0. Okay, so force itself is 0. So W net, work done by net force, is F net times displacement times cosine of angle between them, right? So when force itself is 0, work done going to be automatically 0. That's one way to look at it. Another way, if you like, there are two forces acting, and we found the work done by two forces individually. Remember, we had this here. So one was positive mgh, another one is negative mgh. When we add them together for the total, becomes 0. That's another way to look at it. If you are asked to find what is W net, and basically that is work done by net force. So either way is perfectly fine for doing it. Okay. So now those were in the vertical reduction. And there can be forces acting in, displacement could be in horizontal direction and forces could be acting something like that, several direction. So you can always use the same idea. Now let's talk about situation where object is moving in inclined plane that has some angle alpha. And for now, let's forget about this, okay? So there is friction. So because of that, there is friction force. Normal force is always perpendicular to the plane by definition, right? And this is mg. So those informations are there, and this angle is alpha here, okay? So now I'm asking you, oops, what is question? I already run this. The question is, what is the work done by normal force in this case? So draw force displacement and figure out angle, and from there figure out the work done, okay? So I'm giving you total 2 minutes this time. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so we are looking at this question there. Let's see what we got here. So we got all of them, including one that is not even in the choice. Okay, so what is correct answer? How do I figure that out? So work done by normal force. So we are just interested in this. And displacement is also shown here. Normal and displacement. See, the normal is perpendicular to the plane. Displacement is along the plane. So the angle between them is 90 degree. So work done is FD cosine 90 degree. So here F is the normal force. Okay? Cosine 90 makes it 0. So that's why C is the correct answer. So a lot of you thought, okay, this is correct answer, or this is correct answer because this looks like just the definition of work done, right? But remember, this theta in the work done is, this is going to be correct only if theta is angle between N and D, the force and displacement. In this case, we know the angle. So theta is 90 degree. We need to replace that. So that's why there is better choice here. How about this one? See, the alpha is not the angle between N and D. So you cannot use that. You cannot just stick any angle you see in the equation while finding work done. It has to be angle between force and displacement. So that's why I'm emphasizing this so much. Okay. So never ever do it without drawing the force and displacement. Okay. Figure out the angle that way. So I'm making another question here. Work done by friction force. Let's see what other choices I can have here. Maybe I don't know exact answer, so let's say none of them. Maybe you will find something else. So now we are pulling on this question here. So I'm opening the poll and you have 1.5 minutes to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Nobody chose D. So A, B, C looks like staircases. Interesting. So F is along the plane in that direction, as we can see here. And D is along the plane, opposite direction. So the angle between them is 180 degree. So the work done by friction force is the friction force times displacement times cosine of angle between them. The cosine of angle between them is -1. So that makes it negative Fk times d. So yes, it looks like C is correct answer in this case. Okay. Again, the alpha wasn't the angle between Fk and d, so that's why you cannot use that. Okay. So now, if we look at carefully, in this problem, friction coefficient is given rather than friction force itself, okay? So maybe it's a good idea to expand further. And we know kinetic friction force is friction coefficient times normal force, okay? So that's what we are using for friction force, and D is already there. So now there is normal force, need, and can we figure out normal force in this case? The normal force is here, okay? So let's say the mass is given, an angle is there, right? So mass is given, angle is given. So can we write the work done, sorry, the normal force in terms of those, okay? And for that, we need to draw a free body diagram or complete the free body diagram over here. So this is at inclined plane, so I like to draw like that. And of course, the normal force is in that direction, and there is friction force in that direction, and then weight vertically down. And we know this angle is alpha. This is the angle of inclination. So now this force is along the plane, so we can choose one axis in that direction, and another axis is going to be this. So we see these two forces are lined up with this axis, but the mg is not. So for that, we can use this angle as this angle. Oh, not theta, it's alpha, right? So alpha given. This is alpha. So that means this component going to be mg cosine alpha, because that's the adjacent side to this angle. Another one going to be this side, which is mg sine alpha. Once one is cosine, another one going to be sine. We know that, right? So now to find normal force, we can just look at here, and we see normal force is balancing that mg cosine alpha, or we can say, okay, net force along the y direction is 0 because it's not accelerating in that direction. So positive n minus mg cosine alpha, 0 means n is mg cosine alpha in this case. So this n over here can be replaced by mg cosine alpha. That way, the work done is in terms of the things we know. Displacement is shown there, it's given, mass is given, this angle of inclination is given. Okay, so that way we can complete this. And there can be one more thing you could be asked, since there is weight. So how much work the force of gravity is doing, right? So to find the work done by force of gravity, we need this angle. This angle is not directly given, okay? So maybe we cannot just use mgd cosine of angle between them, because we don't know the angle between these two, okay? If this angle is known, then yes, you can do that. And that's going to be 90 minus alpha. So that's one way to do that. So that's going to go there. Then it's going to be cosine 90 minus alpha. Cosine 90 minus alpha is what? So for that, we need another trig. But there is alternative way of doing it as well. So for example, what is work done by mg? So since we don't know this angle, rather than finding work done by mg, we can find work done by its components. And once we have the work done by these two, we can add them together. That's going to be same as work done by the original force mg, okay? And see, there is this angle between displacement and mg cosine alpha is 90 degree. So if I want to find that, I have mg cosine alpha and displacement, and by construction this angle is 90 degree. Remember, this normal is perpendicular to the plane, and this mg cosine alpha is just opposite, so it is also perpendicular to this plane. So this angle is 90, means theta is 90 degree. So whenever that happens, work done by that mg cosine alpha going to be the force itself, mg cosine alpha, and d and cosine of angle between them, which is 90 degree in this case. So because of this being 0, this work done by that component is 0. This force is perpendicular to the displacement, so that means work done by it is 0. So that means only mg sine alpha is doing the work. Okay, so we can find the work done by mg sine alpha, and that's going to be the work done by mg as well, because this one is doing 0 work here. So it's like you have two hands. Sometimes you may be working with both hands, but if one hand is not working, then work done by you going to be equal to work done by just one hand. So this mg sine alpha is like one hand here, because mg cosine alpha, another hand of yours, in this case of mg, is not doing the work. Okay. So if I want to find sine alpha, so I'm going to just use this portion here. So what I have to modify is that this time this is pointing this way. So that is mg sine alpha. So that means the angle between them is now 0 degree. So because of that, this equation becomes mg sine alpha, the force, times displacement, times cosine of angle between them, and this is positive 1. So that gives me positive mg sine alpha times d. So that is the work done, and that is same as work done by gravity as well. So there are different ways you can do it. So hopefully with all that, I covered the, all aspects of finding work done in different kind of situations. Okay. Now with that, so after work done, we said, okay, net work done is equal to change in kinetic energy, and kinetic energy is defined as half mv square. And then we also learned that work done by gravitational force gives us change in gravitational potential energy, and gravitational potential energy is given by mgy. Y is vertical position from some reference point or reference line, right? So that's what we learned. And once we have both of those, we can start using conservation of energy. And that's what this question or this problem is about, okay? So there, I have discussed how to use conservation of energy to solve any problem in detail, okay? In the class before and in the note. And here, let's look at this particular situation. Here, this person starts from here and gets out. So that's the final speed we want. Okay. So to use conservation of energy, like kinetic energy has a speed. So for final, we need final speed. And for initial, we need initial speed. So that means final and initial. Where is final? Where is initial? We need to assign that. So that's why we sketch the situation here. Starts from here, that's initial, and this where this lives, and that's what the speed we want means. For us, that's going to be final. We don't know how far this person going to go, what's this going to do, but what we are interested is with what speed the person exit the ramp, right? So that's why this is our final. And now to measure the position for the potential energy mgyi or mgyf, we need this to find the yi and yf, we need reference line, okay? And reference, usually it's easier if we choose either at initial point or final point. Usually height is measured from this bottom, so that's what I'm choosing. But of course, you can also choose reference right here at the top if you like. Okay. So these things you want to mark always while using this conservation of energy to solve problem. Okay. So once we have that, see, I'm writing these values. Since our reference is right there, yf going to be 0. And yi is this over here, which is same as whatever the height is. And that height is given, which is, it says, vertical height of the ramp. See there? So that means it's whole thing there. And that is 4 meter. And that's what I am writing, that one there. Okay? And it says skateboarder start descending a curved ramp from the top. So that at the beginning, speed is 0. So that's why we can write pi as a 0. And we are looking for speed at this final point of our choice, means Vf is what? Okay. And conservation of energy tells us that we can write something like that. Total final energy is equal to total initial energy. So in this case, there is no friction information. It says, oh, there is, say negligible for rolling thingy. Okay. So we have kinetic final plus potential final, that gives us total final is equal to same thing for the initial. And then you can plug in numbers and solve for the things that you are looking for. Okay, so that's how we use conservation principle for conservation of energy principle for any problem that is, solvable using this idea. Okay, with that said, now it's your turn. So what is the speed here? Okay. So looks like we should be able to do it in 2 minutes because most of problem we already did here. Okay. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So mostly D. I'm guessing that is correct answer. But let's take a look. Final here position we said was 0 because we chose reference there. So that's it, 0. Initial velocity is 0. And we are looking for this. Yi is h. So that means it is half mvf square is mgh. So now to solve for this, we want to get rid of these here, but looks like m cancels here. So 2 goes and multiplies and becomes 2gh. That would be bf square. So bf is under the square root of that. So that's why D is correct answer in this case. Okay, so I chose that already. So we're gonna leave it here, and next class we'll start from impulse and momentum. Okay. So I'll see you next class, folks, next week.